Okay, so today what we have to do is talk about a variety of topics. If we were in a normal semester where we were to deal with, have a couple more lectures into it and a couple more opportunities to do some example problems, there are a lot of problems that I could do. But we really have to talk about some concepts here as we get going here. And the first thing I'm going to bring up to you is that idea of enthalpy. And you've seen this word before, but enthalpy. Enthalpy is basically a definition that we have. Enthalpy, we're going to call it H, capital H, and enthalpy is going to be equal to internal energy plus the product of pressure times volume. That's all it is. It's a definition. And the thing is, when we see this, we're going to see these terms kind of grouped together many, many times in thermodynamic analysis. And so we said, instead of keep calculating them over and over again, since we see them all the time, let's call it enthalpy. And so that's what we do. Now, these are all properties. Internal energy is a property, pressure is a property, volume is a property. So that means that enthalpy is a property. And we can put it on a unit mass basis. So we divide by mass, and we can say that lowercase h is equal to lowercase u plus pressure times specific volume. So this is specific internal enthalpy is equal to specific internal energy plus pressure times specific volume. So all those specifics come in there when you divide by mass. We can also, if we wanted to, take this equation up here and divide by number of moles, we could get that on a molar basis. I want to make sure that H doesn't look like an N. Is equal to U bar plus PV bar. And we haven't talked a lot about molar basis at all yet, but I just want to keep telling you about this over and over again. Okay? Now, there's one thing I do want to make sure that we're aware of, and that is the quality equation that we dealt with still applies, HF plus X times HG minus HF. This still applies for enthalpy just like it did for internal energy and specific volume, and we're going to use it many, many, many times. But what we can do often in enthalpy, because we deal with it quite a lot, is this Hg minus Hf, we call it HFG. Now that doesn't make a lot of sense here. It's Hg minus Hf, and we call it HFG. It's kind of like 1 to 2. When we want to find out what the difference in delta is from 1 to 2, we take 2 minus 1. Same thing here. This is kind of like 1 to 2, and then we have here 2 minus 1. HFG is called the enthalpy of vaporization. The enthalpy of vaporization. It is how much enthalpy you need to vaporize to go from a liquid to a vapor. And so I'm going to pause for a second. Well, my document camera is not working today, so I have to go back and work on it. But I want to show you on your properties tables here. This is terrible. There is going to be an enthalpy column. There it is, enthalpy column. And notice here, saturated vapor, saturated liquid, and then right between those is going to be HFG. HFG, it's evaporation that's happening there. Basically, all it's doing is taking this number and subtracting it from this number and putting it right there in the middle. They're doing some math for you. It's very convenient of them to do that. It's very simple. You can do it yourself. But they call it evaporation. Same thing as vaporization. And that's what it's there for. And that's going to be very useful to you, especially when you're doing this calculation over and many times throughout the semester. Okay, let's move on now and understand when this might come up with you now. It's going to be very useful. Enthalpy is going to be very useful in chapter 4 when we talk about open systems. But there is a special case, and let me make sure that you understand this is a special case. A special case when you might use it with a closed system. And so let me describe that special case here. Let's look at the first law. The first law is going to say that delta KE plus delta PE plus delta U is equal to Q minus W. Okay? And what do we do here? Most of the time we say kinetic energy, potential energy effects, they're negligible. We're going to get rid of those. And so we end up with our equation that looks like this. Mass times internal energy 2 minus internal energy 1 is equal to the heat transfer minus the work. Okay? Now here's where our special case comes in. This is our special case where it comes in. Let's say we have constant pressure work. Okay, you know when I use this crazy rainbow pen, there's a special thing we have to think about. Okay, constant pressure work. Remember, work is going to be integral from 1 to 2 of P dV. Constant pressure work is going to give me pressure times V2 minus V1. Okay? And I'm going to insert this into this equation here. And when I do that, this is what I get. Mass times U2 minus U1 is equal to Q minus pressure times V2 minus V1. Okay? Let me take this term here, and I'll move it to the other side of the equation. Move it to the other side of the equation, what do I get? I get mass times U2 minus U1 plus pressure times V2 minus V1 is equal to our heat transfer. And now let me put some things together here. I can say, well, I can write this as, before I put this together, I can write this as mass times pressure times specific volume 2 minus specific volume 1. Okay, so now instead of using volumes, I'm using specific volumes. And if I do that, and now I'm going to put things together, I'm going to take out a mass and say this can be equal to U2 plus PV2 minus U1 plus PV1 is equal to my heat transfer. And lo and behold, what do we have there? What is U2 plus PV? What's U plus PV? That is enthalpy. And so now I can write this as mass times enthalpy 2 minus enthalpy 1 is equal to heat transfer. So, in certain cases, when you're dealing with a closed system with constant pressure work and you're trying to solve the first law, you can organize the equation such that you have the term U plus PV, internal energy plus pressure times specific volume, and then that becomes enthalpy. Now, why do we want to do that? Well, it saves us a whole lot of time if we are doing an equation looking things up, because look at this. Instead of looking up 4 things in our table, now we're only looking up 2 things in our table. Okay, and that can save us a lot of effort. Now we have to do some algebra, of course, but I want you to remember this special case. It is not the rule. It is not the rule. It's often the exception to the rule, but you'll see it show up a lot, and it's a helpful thing to work with. Sometimes you'll get into an equation, and the main times that I see that I want to use this is I'll be working on a problem and I'll say, man, I don't have enough information to look up U2 P2. U2 V2. I don't have enough information. And when I think I don't have enough information, how can I solve this? I think, okay, can I simplify this and get less things, less variables? And this is one of those ways to do that. So pay attention. Keep it in the back of your mind, and be ready for that when you see it. Okay, so that's end up our topic about enthalpy.